Hello everybody and welcome to this new amazing lesson in which we are going to learn about the data structure linked list. In this video we are going to find out what is a linked list, what operation it supports and how it is implemented, and then we are going to see some real-life applications of the linked list. So let's start. A linked list is a linear collection of data elements whose order is not given by their physical placement in memory. If you remember, this was the case with the array, where the elements are stored at consecutive memory addresses. Instead, each element of a linked list is stored at some memory address, so they are not necessarily consecutive, but each element points to the memory address of the next one. In its most basic form, each node contains data and a reference, or in other words, a link to the next node in the sequence. As an example, this is a linked list of size 4 in which the data inside each node is an integer and also a link to the next node. And the data type of this link is a pointer. So in each of the first 3 nodes, the link points to the memory address of the next node. And in the last node, the link points to null, just to denote that this is the end node of the linked list. So the nodes can be implemented as classes which have 2 properties, next and val. Let's see how the class node looks like in JavaScript. As you can see, inside the class we have a constructor which takes one argument, which is the value that should be stored in that node. Could be an integer, could be a float, could be a string, it doesn't matter. This is because when we create new nodes, we usually know the value that is going to be stored in that node. But we usually don't know what is going to be the next node. So this is why inside the constructor, we set the next link to be null. And once we know the next node, we will usually set it inside the main algorithm. If you know for sure that whenever you create a new node, you will know what is the next node, then sure, have another argument in the constructor and also set the next property. If not, we usually set it externally in the main algorithm once we know this information. This is how the class node is going to look in Python. It's the same. We also have a constructor with one argument. And this is how it looks like in C++, where, as you can see, we can use struct, not necessary class. And I like this definition because, as you can see, the data type of next is node star. So in C++, you can clearly see that the link is a pointer. Every linked list is determined by its so-called head, which is the start node. Knowing only the head is more than enough for us in order to be able to access the nodes of the list and also manipulate the list. Let's see how we can iterate through a list. We will use a node pointer, which is initially equal to head, and while that pointer is not equal to null, I can access the value in that node. Let's say I want to print it, and then I can move to the next node using node next. Now let's see what operations are supported on a linked list and how we can implement them. The first one is adding a node in the list. Actually, now I think inserting is a better word, as we can insert a node wherever we want in a list. In order to do this, we will first need to know where to insert that node and also what is the value of that new node. So we can write a function named addNode, which takes 2 arguments. The first one is a node pointer, which tells us that the new node should come after this node in the linked list after the insertion. And the second argument is, of course, the value in the new node. Let's say that we want to create a new node, which will store the value 6, and then insert it after the second node of this linked list. We will first create the new node using the constructor and store its memory address into a pointer named new node. Then we need to link this new node to the one that comes after the argument node. So new node next equals node next, and as you can see, the link is created. And then we need to link the argument node to this new node. So node next equals new node. As you can see, the link from 3 to 9 was erased, and now the new link is 3 to 6. There is a special scenario in which maybe we want to insert the new node to the front of the linked list. In this case, the value of the argument node will be null just to denote that this is the scenario. And we can treat it separately and say if node is null, then let's create the new node using the constructor. Then we should link this new node to the current start node, which is the head. So new node next equals head. And as you can see, the link is now created. And now, of course, we have a new start node, which is this new node. So we should set head to be equal to the new node. And that's it. As you can see, all we do inside the add node function, no matter what is the scenario, is create a new node and then assign some pointers to the links. So inserting a node in a linked list takes constant time. The second operation we can perform on a linked list is removing a node. And in order to do this, we need to know what is the node that we should remove, right? So let's have a function, remove node, which is going to take only one argument, which is a pointer to the node that needs to be removed. We have one special case here, and that is when the node we want to remove is the head. All we need to do here is set the new head to point to the node after the initial head, and then just delete the node so we can release the memory it used and maybe use it for other things. If node is not the head, then we need to know what is the previous node in the linked list. So let's say we write a function that will find the previous node of some node in a linked list. And once we know this previous node, all we have to do is link it to the node that comes after our argument node. And then, of course, delete that node to release its memory. The problem is that finding the previous node, it's not so easy. We actually have to start from the head, and while our current node doesn't point to the node we are looking for, we have to go to the next node and try that out, and go to the next node and try that out, until we finally find the node which links to the node we are looking for, and then, of course, we will know that that is the previous node. So as you can see, in order to find the previous node, we actually need to iterate through the linked list. And in the worst case scenario, we are going to iterate through each and every node, so the time complexity of this function is big O of n. And this will also make the remove function big O of n. So yeah, this depends on the problem. Of course, if the problem somehow gives you the previous node whenever you want to remove a node, that's fine. You can do that in constant time, as you don't have to iterate through the list in order to find it. But in most of the cases that won't happen, and you either have to look for that previous node, or maybe you have to find a node which has a specific value, and you will have to iterate the list in order to find the node first. And while looking for that node, you can also have another pointer which will always point to the previous node. So from one traversal, you can tell what is the node and also the previous node, but obviously that's also big O of n. Alright, and this is all the technical information you need to know about the linked list. Some real-life applications are implementing stacks and queues, storing graphs in memory, dynamic memory allocation, or for example, music players and visited web pages history if you want to go next and previous and stuff like that. So yeah, as you can see, the linked list is most often used in order to build more powerful things like stacks, queues, doubly linked list, graphs, but we have a lot of coding questions which involve linked list. They are often asked in coding interviews, so we need to make sure we can solve those problems, and that's indeed what we are going to do in the next lessons. See you there. Bye.